Before the workshop starts, we're going to show you how to navigate through the video. Below the YouTube video is the Show More button. Click the Show More button to reveal the index. You can skip to the point that you want in the video by clicking the blue time link.
Teaching and learning plans, first of all, the applications of geometric sequences and series. Okay, there's the beginning of it. Now, just to start off the day, this particular problem here that I'm going to put on the board. Now, I don't want you to use a calculator. I don't want you to use the compound interest formula. There's 451 years between 1562 and the present time. Now, this article was in 28th July 2012. The mayor of Wittenwald, right, which is a town just outside Berlin, right, found this promissory note, right? And back in 1562, the town had lent the German government 400 guilders, which is about 166 euro, right? How much do you think, after the 451 years, and at a 6% interest rate, right? How much do you think now the German government owe the people of this town outside Berlin, right? They went to the German government and looked for the money. How much do you think the German government owe? A figure off the top of your head now. You don't know compound interest formula, right? You don't use calculators, right? Figure off the top of your, write it down on the back of something, the back of a sheet of paper there, right? Take a guess to see how much. Take a guess. Okay, you have to figure it down. If you look now, 100 euro at 20% interest per day, exorbitant interest rate per day. There are companies out there at the moment offering that. I won't mention any, seeing as I'm on camera, right? I won't mention any, but there are companies. You'll see ads on the telly every day for them, and they offer a very small amount of money at a huge, phenomenal interest rate. Okay, so 100 euro at 20% interest per day. If you copy that diagram, you see the diagram, there are 20 little blocks there altogether. Copy that diagram onto the acetate sheets, onto these, right? Okay. And then, when you have that done, what I want you to do is as follows. You want to, each block represents 10 euro. There are 20 blocks, so there's a total of 200 euro altogether there. You want to colour in. You see this here? Each block represents 10 euro, shade in 100 euro. And then answer the questions down along here. It's 100 euro at 20% interest per day now. So what we're doing with this is we're representing compound interest visually for the students in class, and we'll talk about their misconceptions now in a minute, what they have. So have a go at that. Now, some students, and I went around and I saw some of the teachers actually here in this room doing this as well, right? There are other ways of representing it. There's another way, which is actually a nice way of doing it, okay, right? Getting 20% of each block and then adding all the blocks together, right? And then doing the same again for the next one, right, okay? Getting 20% of the bits that are there, right? And then adding all those. And again, you end up with the very same diagram as the first one. But that's another representation, right? I've seen actually students doing it, right? Tried this out in a class out in Jarlath as well, just to see how it would go. But I've seen them filling in, shading in that, initially for the first 100 euro, and then taking the bits of those, right? Okay. So there are various visuals again, and it's important actually to show them there are various ways of doing it, representing it. Now, this diagram is up here on the board. It says use the whiteboard that you have there to graph the amount owed against time elapsed for the first 4 days. You already know that day 0, you have 100 euro. Day 1, you have 120 euro, isn't it? Yeah. And day 2, you have so on. You nearly know the couples already at this stage. But for the first 4 days, Interesting here, when this was being developed, I kind of said here that why not label the axis? And somebody said, don't label the axis, because you can scaffold the question differently. If I had a foundation level class or an ordinary level class, I would actually label the axis. I'd have the number of days along here, I'd label it for them, and then the amount of money up there at the side. And so you're helping them along in the question. But with a higher level class, I just leave it, just graph, see what happens, right? I'll leave you at that, but I know it's going to throw up some misconceptions, even among ourselves. When I did this initially, I made a mistake in this initially when I started off. So have a go at that, right? What you want to do is plot for the first 4 days, right, the amount of money for the first 4 days. So you have 4 sets of couples. And again, I would say label the axes again. You can use the back if you want to.
That was only day 2, yeah.
Here is maybe the completed graph for you. Right. That graph there, so we can say that exponential functions, a very important fact about exponential functions is that the multiplier is a constant, right? Or the ratio of 1 divided by the previous one, 1 divided by the previous one is a constant always, okay? So the ratio is a constant. These are exponential functions, as we see here. Change and change of change have a common ratio, so it is an exponential relationship. Okay. There's a graph of a linear graph. There's an exponential graph. Look at compound interest, 100 by 1.2 days, right? Okay, 100 plus 20 days. This is linear. This is exponential. Okay. Right, let's look at a pattern. What would the formula be for day 20? What do you think? 100 by 1.2 power of 20. Correct. Right? Perfect. That's perfect. Day n. Now here we're beginning to generalize. What do you think it is for day n? To the power of n. Yeah, that's enough to say to the power of n. We know it's 100 by 1.2 to the power of n, as we can see there. Now, a couple of variables, if we change it around, instead of using €100, if we use 150, it'll be 150 by 1.2 to the power of n, won't it? Is that okay with everybody? Mm-hmm. What if we started with 527? Same question there again. What is it? 527 by 1.2 to the power of n. And then if we increased it to 30%, here is a major misconception, I think, in classrooms. In my classroom anyway, when I'm doing percentages with them. If I do 20%, and they might come in from another class, and they might say, oh God, we know what that is. We multiply by 0.2. I say, fine. Multiply by 0.2, and they call that multiply by 0.2 to get my 20%. The difficulty is if you write down 2%. Right? They still write down multiplied by 0.2 or 0.2 again. Do you follow that? They have a misconception there. So when you're actually teaching the fractions, decimals and percentages, take it slowly enough with them. They might have it done in national school already, but you actually go over it again. And when you're dealing with percentages, it's 20 parts of 100, 2 parts of 100, and then work out 20 parts of 100 is 0.2. 2 parts of 100 is 0.02. So be careful with those. And so that's what I'm saying there. If we increase by 30%, the percentage will be 100 by 1.3 to the power of n. Is that okay? And then by 100%, which is a nice one to throw in, it'll be 100 by 1 plus 1. Is that okay? Which will be 2 altogether to the power of n. And here it is, right? This is what we've been using. And this was the whole aim of that particular class, was to introduce the compound interest formula seamlessly. Rather than what I used to do before, I used to write down, when I taught this stuff before in junior cert level, you'd go, and I'd use the old formula, right? Amount equals P into 1 plus R over 100 to the power of N. Everybody in this room remembers that formula, right? Because that's the one we had when we were going to school, or that's the one we had taught, right? So now the formula is F is equal to P into 1 plus I to the power of T. On page that. Now what I would have done with this before is, okay, I'd give them examples, €100 invested for 3 years at 2% and get them to fill in or substitute into the formula and work it out. Again, you take it slowly with them initially. You do 1 year, 2 years, 3 years, and you do it out the long way, right? By the way, to the power of 3 at foundation level, but it can be still asked, the formula can still be asked. So if we look here, here's the formula in the log tables. Notice that I now is R over 100, okay? There's the formula in the log tables. Final amount or compound interest is the principal 1 plus I to the power of T. It's on page 30 in the, is that 30? It is 30 in the log tables. You know the way the old log tables, you just remember all the pages, right, okay? The handy angles on page 12, right, okay? So there we are. Back to the question we had initially. What answer did you write down? What answer did you write down? Right, do it now using the compound interest formula. Final amount equals P, which we started off with, €166. That's what we started off with. Into 1, what interest rate was 5% as far as I recall, wasn't it?
6.
Or was it, no, was it 6%? Was 6%?
Yeah, 6%.
Spot on, 6%. And so therefore that is 0.06, be careful of that again, to the power of, what is it, 451, isn't it? You have calculators in front of you. Now we're allowed to use the calculators as teachers, right, okay? We can use the calculators now. And at this stage I would introduce the students to the calculators to show them how to work this out in a calculator. Somebody has worked it out here on this, and it is, I've no glasses, but here 4.29 by 10 to the power of 13. Oh, your eyes aren't that bad yet, right? Okay, 10 to the power of 13. Okay, there we go. I would take the, that's in euro now. I would take the opportunity here in the classroom. I would say, you're talking about big numbers. What the hell is that? What is that number, right? Okay. 10 to the power of 6 we know is a million. 10 to the power of 9 is a trillion, right? 10 to the power of 12 is a, 10 to the power of 9 is a billion, and 10 to the power of 12 is a trillion, right? That's what we have in Europe anyway. I think they're different in America, I'm not sure, right? Okay, so if I want to change that to 10 to the power of 12, and that would be 42.9 by 10 to the power of 12, wouldn't it? So it's 43 trillion euro. There you go now, Angela. Give us that, right? Okay. 43 trillion euro. That is the power of compound interest. All right? That's an idea to introduce. Again, you'll come across opportunities like this in class and grab them as best you can. Hey, can I bring in something else here? Don't just kind of try and keep it all uniform. Oh, I'm doing compound interest here. I'll stick with you know, big and small numbers here is very, very important to mention there in that particular one. So that's the trillion, right? What is it? 43 trillion. Einstein. I actually looked up the quote a couple of weeks ago. It's actually, he's credited with 2 quotes on compound interest, right? The first one, the most powerful force in the universe is compound interest. Compound interest is also the 8th wonder of the world. He who understands it, earns it. He who doesn't, pays it, right? Well, I think the second one is a better quote. The only similarity between myself and Albert Einstein is, right, that when I went to Madame Tussauds there a couple of years ago, he's the same height as me, right, okay? Right, he's not very tall, all right, okay. So there's Albert Einstein, right? And there is that. Now we're back to the same teaching and learning plan again. Now why did I get back to this? It's to try to encourage teachers to use the teaching and learning plans. All the teaching and learning plans are now up online and they're interactive online. What do we mean by interactive? Well, we mean as follows. If you're going along there, and there's the lesson that we were actually doing from the T&L plan on geometric series and sequences. You have that activity sheet up for the students on the data projector. But if you actually freeze the screen here, right, okay, if I see freeze screen, I have the freeze screen on. I just pointed at the data projector. Freeze screen is on. Now when I come over here, I can click on the tab here. You don't see anything happening, but look, if I hold this up, watch it, see that there? There's a whole different screen, the whole different thing on the screen itself there. And the screen itself there is the instructions on what you need to do as a teacher, right, to carry out this lesson. And so you have the tabs with the instructions on the side, and you can freeze screen, you can be up at your desk, you can look ahead to see what's actually coming next in the lesson, all right? All of the teaching and learning plans, thanks to Neil Doherty in Donegal, he did them all. He did a powerful amount of work on actually doing them. Okay, moving on from that, reducing balance I want to look at now. This is again from the same T&L plan. There's two questions on the board there. I asked the other day, what's the similarity and what's the differences in those two questions? What's the similarity in those two questions? Similarity. Do you know what somebody said the other day to me? They're both dealing with snow. And I said, correct. Huh? They're both dealing with snow. But the difference is huge. The first one is linear, and the second one is exponential. Now, linear is grand. You wake up in the morning, 12 kilograms of snow outside your door. You get the big shovel, scoop it away. Each time you're scooping away with the big American shovel, I call it, right, okay? You can see here that we'll have 0.5 kilograms on each shovel. So the number of shovels I will take will be, what do you think? 24 is correct. Here's someone saying 24, because I have 0.5 into 12, so 24 shovels altogether. That's linear. It's depreciating linear. We're taking away the same amount each time. Look at this one. This is different. Ooh. That's compound depreciation. That question arose in the junior cert paper, higher level paper, I think in 2006, as far as I recall. There's a bit of controversy about it in that the percentage rate was a bit difficult than they were normally used to. It was depreciation rather than increasing compound interest, right? Give your answer correct to 2 decimal places. Why is it depreciation? Well, you start off with 12 kilograms snow and it goes down by 0.2%, and then you have a different amount and you're going down by 0.2% each time. So it's compound depreciation. And actually the formula F is equal to P into 1 minus I to the power of T. That's in the log tables as well, or the new formula tables as well, okay? On page 30 as well. And F, the final amount, what do you start off with? 12 kilograms, don't you? 1 minus I, and I would do this slowly as well in class, 1 minus I, and so it's 0.002, isn't it? Yeah. Be careful of that. And to the power of T, and the time interval or the time span is 3. The time span, right, you're told is in minutes, so therefore that's 3. Now time span can be years, it could be minutes, provided you're using the same thing each time, right? And so therefore working out that should give you the amount of snow of the snowman that will have melted. What would be the mass of the snowman? It will give you the mass of the snowman after 3 minutes. Okay, again, linear and exponential. And you can see here on page 30, it's there on page 30. Rather than just saying, go to page 30, fill into the formula, take a question like that to help them introduce it, okay? So, the last thing on this T&L plan that I want you to look at this morning will be as follows, this one here. Save you the hassle of reading the question here, and the question is on the bottom of page 2 on the activity sheet, but I'll read it out for you as follows. Right, set the scenario. David and Michael are going on a school tour and they both have to pay €600 on the school tour. You know the way when you're organising a school tour, you have to have the money up front, right, for the travel agent, right? So they both had to pay out the €600. So they both went to the credit union, they borrowed €600. They borrowed €600 and they hope to pay it off over the next year, right? But David said that he had part-time work at the present moment in time and he could pay off €100, right, each month for the first 4 months. That's what David said. But Michael said, hold on, I have no part-time job. I can only pay off €60, right, for the first initial time. But at the end, I might get a part-time job coming up near Christmas and I'll be able to pay off €100. So you have different payments, different payment schedule. And this is very important in all of this. What we're trying to do is make the students financially aware. We're also trying, one of the learning outcomes in the syllabus is trying to make them statistically aware as well. But we need to make them financially aware as well. Look, there's the start of it, right? Have a go. It is a thing, though, that you would actually go through in class with them because you want them to practice our maths. Right? You want them to practice our maths. There we are. All right. Right? Is that okay? Now, in the teaching and learning plan on this, you get the students to actually go through all those figures themselves. And it is important they go through themselves. It's important they gain the skills of using calculators, filling into tables, looking at repayment schedules. It's a vital skill for them. Now, the one lesson that when we're going through this, the one lesson that I kind of gleaned from all of this was, very important teaching aspect was, this, we look at tables sometimes, and the new approach is the multifunctional representational approach to algebra. That is looking at graphs, tables, right, okay, looking at different representations of different things. But look, there's a representation of all that data on a graph. Now, I'll go back up again. There's the graph. There's the table, which the students have completed. Which do you think is preferable? Which do you think you would glean the most information from straight off even looking at them?
Graph.
The graph, you say, okay.
But the table shows you instantly how much interest they pay. That's what I'd be interested in.
Absolutely. When I looked at those two when we were actually developing this, I said, hold on a minute, I think that the actual table is way better. I can't get much out of the graph. Okay, if I actually look deeper into it, I could get something out of the graph, but I think the table is a far better representation. So sometimes graphs aren't always the best representation of data. Tables can be sometimes. There's a table. You can glean a huge amount from that table by scanning through it. You can have a huge discussion in class about what's happening here. And open it up to the class and get the discussion going. Who do you think is in a better position, David or Michael?
Dave.
David, right? Obviously David is paying back the loan a lot quicker, isn't he? And why is David paying back the loan a lot quicker? Because his initial payments are bigger than Michael's. You can look at the bottom lines, and look at the bottom line on a table is always interesting to look at as well. And when you actually do this here, David paid that amount of interest, 36.25, but Michael paid 46.38 interest. So you can look straight off at those two figures, and they actually stand out for you. And in most payment schedules, look for those bottom lines. And it's important to emphasize to the students, from a financial education point of view, to look at the bottom line and see actually what you're paying back. And the other thing is that look, he has one extra payment to make, hasn't he? And so, like, to me, that's okay. It is a representation, but to me, I can gain a lot more information. You can see David has a money paid off in 8 months, and Michael will take 9 months to pay it off. Okay, you can see that there. But apart from that, it doesn't actually give you the exact figures, and you may be better off with exact figures when you're dealing with financial stuff. It's just there, right? Understanding compound interest is a life skill, right? And understanding financial implications of loans that you take out, or you putting money into a bank is important, or money into a credit union, what interest rate you're getting. That's a huge life skill. And it's a life skill that actually students in class, they seem to thrive on. They love when you start talking about money, right? Okay. On Google, just type in payment reschedule and you will come across, look, here's the first one. We'll say, I know it's in dollars now, but forgive me for that, right? I did this last year, it was there, the 1st of the 1st, 2013. But look, that's in dollars, $200,000, let's say it's euro, right? Interest rate 4.5 on a mortgage for 20 years. Right, repayment schedule, 12 payments every year, so monthly, and the actual schedule repayment per month is 1,265, which is about right now at this stage, isn't it? For most mortgages at this stage, I think it's 4.5 around that anyway, unless you're lucky enough to have a tracker mortgage, or which thank God I have. Right, okay, but there we go. Right, there, that's fine, and there's your total interest paid. Bottom line again, look at the interest paid. Here is loan amount. Here is same thing again, 4.5, 20 repayments, 12 payments a year. There's when interest taken out, but you're paying an extra €200 a month. And when you've, like Michael, like David up there, he's paid off early, right? Paying off €200, do you see? Look, payment there, and the maths are easy enough. You could actually get the students to do out this or replicate that. Per year, and so on. Well, difficult if you're doing a amortization form at Leaving Cert higher level, they should be able to do it because that's a mortgage repayment, right? But unfortunately, maybe, what do you think if to just compound it, how much would that be? But look at here, 80,735, 103,600. So if you pay back something extra every month, you will certainly have less interest to pay, and you'll have paid it off in a quicker time. I wish somebody had taught me that when I got out of mortgage, right? Just before coffee now, this one here. It is functions. You may say this is a totally different section. In actual fact, it's not. But we'll look at functions first of all. Normally, when I taught this in class, I would build the students up a week beforehand, and I'd say to them, I was in McDonald's in Galway last week, hardware store, and I came across a fantastic machine, especially when you're living in a local area. If you mention local name, John Kelly, you know John Kelly lives down. John Kelly called me over, he said, can we come over here with a fantastic machine for you, right? So I said, a minute I saw it, I bought it, and it's called a functions machine. And I built them up for a week beforehand. I said, did you bring it in? No, jeez, I forgot it, it's at home. And then the day I would be doing the functions, I'd bring, did you bring it in, sir? I was down the staff room, I go down, don't, not a word now, not a word, they'll all be given out, not a word. I'd bring up, and all it would be a cardboard box, right? And I'd have it fancied up a little bit, right? And basically, what I would do, I'd have a slot in the cardboard box, and I'd have cards ready, like this. And I'd put in, I was trying to work one the other day, but I put in into one slot and shh, come out to the other side. Oh, look, the number is after changing, I'd say. She's a magical box. And they'd say, you're joking us now, sir. Of course you are. And I said, okay, but what's the box after doing to the number? I put in a 2, shh, comes out the other side, comes out as 4. You'd have their interest captured. That's all you're doing. And they would say, oh, the 2 is after doubling. I'd say, perfect. And somebody else would say, you added 2. And then the really bright sparks would say, hey, you put in 2, came out as 4, you squared 2. Now, they would really be bright kids, right? You'd pick them out straight away. Good, spot you, right? Okay. But you say to them, well, there's 3 things, 3 suggestions in class. How am I going to test to see which one it is? And they would say, oh, put in other numbers. So I'd take 3, right? I'd shove in the 3 in, and it'd come out as 6. And then they'd say, ah, it's after doubling. But I'd say, well, sure. How am I plug in more numbers and I would have a rake of numbers here ready. I'd even have a letter. Let's see if I put in a letter, will it do? And I'd shove in the letter, and it'd come out as 2k. And they say, brilliant. And they say, will it do the same for money? That's what they say. And I would have ready, I would have a fiver pasted onto some, and the back of it, I'd have a 10 euro pasted onto them, shove it in. Hey, magic, you know. So I'd say, this is a functions machine. And I used to do, and I'd get them then, I'd have a series of numbers ready, and they'd guess what the function was. That was the whole idea. And what you're doing, you're introducing them to the language of it. Inputting a number, output. Input, output. Couples together. You have your input and your output. On a lot of the internet now, type in functions machine, and they're all over the shop, right? I just have one here for you, and I'll just show it, and we'll throw a couple of functions at you. The National Library of Virtual Manipulatives in Utah State University. It's NLVM. If you type that in, Utah University, that's where you'll actually get it, right? And if you look along here, and I go to 8 to 12, which is the equivalent to our junior cert, right? Now, some of these are a little bit hard now. And look, not alone in the algebra does it do functions machine, which is here, but it does transformation, it does coin problem, it does block pattern, base numbers, algebra tiles, algebra balance, right? But it does all probability stuff like spinning coins, tossing coins, spinners, dice, the whole lot. It does rake of stuff there. So here is the functions machine one. Beautiful machine, right? Okay. We take the number 1 and we drop it in. And it comes out as 4. Now your job is to predict what function it is. What do you think? It could be 1 plus 3 or x plus 3. Okay. Could be 4 times x. 4 times 1 will give me 4. We'll have to test other numbers, of course. I hope the first one we do isn't hard. 3 going out as 8. Ah, it's a lovely one, isn't it? Right, it's a lovely one. Is it linear?
Yeah.
How do we know it's linear?
Constant difference.
Constant difference. 4, 6, 8, 10. Constant difference of 2 there. 2, 2, 2. Right? So the rate of change must be 2, mustn't it? Mm-hmm. Let's look at the couples. And the couples are 1, 4. 2, 6. 3, 8. Isn't it? 3, 8. There. So it is linear, we said. Okay, what is it? What did we say the function was? 2x, because it must be 2x anymore, isn't it? 2x plus 2, isn't it? Because the function is 2x plus 2, 2x plus 2. Because when I put in 1, I get 4. When I put in 2, I get 6. When I put in 3, I get 8. There's a huge amount of learning in this now, because I've actually drawn the graph, haven't I? Where does it actually cut the y-axis? At 2. So the start value is 2. And so therefore y equals mx plus c, y equals mx plus c, and so y equals, the rate of change is 2, 2x plus 2. Is that okay? So we know what our function is now. Usually by initiative, or by intuition, they get that it's 2x plus 2. Not by initiative, by intuition, they get that it's 2x plus 2. We can fill in the next one, obviously. It's 12, isn't it? Uh-oh. 12. Suppose I put in 13. And the beauty about it is if you put in 13 and you hit return, they'll say, try again. Right? And so you just put in 12, and then down here, and so on, 12, 14, and then 16, and we know that's correct, right? So hit return, that's correct. An informal introduction into functions in first year. That's what you're talking about. Oh look, there was another one in relation to patterns, and you don't have to give them 100 pattern questions in first year. You give them a couple of pattern questions. This one here in relation to the money box is discrete data, so that when you're actually joining the lines, do it in dotted lines because it's discrete data. But when you're dealing with the sunflower, remember the sunflower one, that's continuous data. There's another connection. That's continuous data, do the full straight line. There's a connection between discrete data and continuous data in statistics. That you're introducing them in first year to the language. But up here, inputs and outputs, they're okay with that, right? No, they're not okay with this sort of stuff. Mathematical language. I used to always say to them, you know, you get a question, they see a question someplace and say, solve for x, where x is an element of r, x is not equal to 2, and I'd always say to them, don't mind that old Faldidal stuff at the end, forget about all that stuff, that's only put in to be mathematically correct. But really I was wrong in saying it. You should really say terms and conditions to every question apply, right? And they know that phrase, terms and conditions apply. So terms and conditions apply, and you should really, in first year, begin to introduce them into mathematical language, depending on the class, of course. D is an element of n. A really good class in third year or in fifth year, or even in transition year, ideally get the syllabus, and where you see, oh, big lot of mathematical, photocopy it, bring it in, and have a talk about it. What do all these symbols mean? Why should there be a separate language for mathematics? Like, that's very important in a mathematics education, because if they're really good kids that go on further, they do maths at a higher level, they need to be into this sort of language. Right? And no better place in a friendly atmosphere of your classroom to start introducing the whole thing to them. So don't neglect mathematical language, basically, right? Even from first year, right? Not too much of it now, but have, you know, those there, right? Here's a quick recap for them in functions. I think these slides are very clever, because when I was teaching this stuff before, I tended to use numbers. I think actually using the pictures, again, picture, what's this they say about a picture is paints 1,000 words, right? Okay. Right, Brian there is married to Amy, right? Okay. And your man is married to your one, right? Okay. And Homer is married to Marge, right? Okay. Is that a function or is that a function? It's a lovely question for class because it's relating to what they know. Well, that is a function.
Dysfunctional.
Huh? Very good. Dysfunctional is right, yeah. Right. Okay. And Kylie is not married to anybody. So it fulfills the two conditions of being a function. Right? Every element here must be used up. Right? And there must only be one arrow coming out of each element here. Okay? That's what it is. If you looked at the old kind of dry way that I used to teach it before, or that we had in class for doing it before, and it was in the books before, would be as follows. Here's a function, 1, 2, we'll say 2, 4, 3, we'll say 9. That was a function, and we said, well, look, the first letter is not repeated, okay? That's what we kind of said. It's a function. Once you look along the couples, the first letter is not repeated. Well, the first letter is not repeated. There's only one arrow coming out each one of those there, right? Okay. And you can't have this one here. You can't have all the elements must be busy here. They must be all full here. So you can't have, we'll say 4 and nothing else with it. It won't be a couple at all then. Right? You can't have that. So, like you can't have, if you do it on the set diagram, we'll have 1, 2, 3, and we'll have 1 going to 2, 2 going to 4, 3 going to 9, and 4 going to nothing. Or as I said, 4 going to nothing. Right? Okay. So 4 going to nothing there. That is not a function now. Here are the conditions. Each man in X is married to a woman in Y. And the second condition, each man in X is married to only one woman in Y. So if both these conditions are true, then it is a function. It's a really brilliant example. I'd be looking for a long time to find a good example of something like this, right? Very relevant, 2012 Olympics in London. Adams, Bolt from Jamaica, Dwight Chambers from Great Britain, Donovan Bailey from Antigua and Bermuda, his brother from the USA, right? They're all the countries they're representing. Here's the athletes, right? In the semi-final of the 100 meters, right? That is a function, isn't it? It's actually a one-to-one, right? Special one. If you do it for leaving cert, it's a bijection, right? And then this is only first year stuff, right? You go on later on, do injections, surjections and bijections. You're building the groundwork for them later on. But that is a function. Great one, right? This is not a function. Why? Look at the 1. There's no arrow coming out of 1. It's a great example. Lane 1 is empty. I don't have to say any more about that. Is that okay? Condition 1 fails. Great example again. Boxing. Katie Taylor won the gold medal, right? The Russian, she beat the Russian in the final. But there was a bronze medal is shared in boxing by 2 people. So that is not a function because there's 2 arrows coming out of the bronze medal. Great example for kids. So there you are. No, condition 2 fails. Is that a function? This is the final of the 100 meters. It is, even though the arrows are crisscrossed every other way. And look at Powell is from Jamaica. There's 3 Jamaicans, Bolt, Blake, and sorry, there's only 1 Jamaican, sorry. From the USA, there's Gay, there's Gatlin, and there is Bailey, Donovan Bailey from the US. So even though there's 3 arrows going, there's still a function. If they're given the picture, and this is where we're trying to get them at, and we'll see later on in the workshop today, that we're trying to get them to get pictures in their heads of functions, and trying to get them to see, to recognize a picture, and try to see can they put a picture on a mathematical function, right? We all know that one, don't we? What is that function? It's a minus x squared, some sort of minus x squared function that goes that away. And a plus x squared function we know goes that away. Right. Is that a function? It is. Now, that one there, we'll look at it. Like the top 3 now would be, the ones on the top there would be junior cert. Maybe that's stretching it, but it is junior cert still. All of those are junior. They'll be leaving cert functions. Or if they're functions or not, they mightn't even be functions. Beautiful test there is called the vertical line test. If you draw a line down here at -2, there's only one place where the function is cut by a vertical line. So it is a function. Is that okay? Mm-hmm. It's called the vertical line test. There's the vertical line test. That is a function. That is not a function. Right? I wouldn't be going too much into that in first year with them, because they won't, right? Okay? They won't, but it's just to round it off for ourselves, really, okay? And then, just after coffee, we're going to be dealing with these. So there you are. That's what we're doing straight after the coffee. All right, okay?